Hello, my name is Stephen Vellick, and today we're going to take a look at the infinitely small universe. It's called quantum mechanics. Now, before I get started, I would like to just mention that this is going to be a very simplified version without any math, hopefully, and it's something that anyone should be able to understand. Let's get started. First, before we talk about quantum mechanics, we have to talk about classical mechanics, which most of you know, but perhaps you don't know that it's called that. Now, this includes Newton's laws of motion, Newton's laws of gravity, the law of conservation of energy and momentum, and classical mechanics has exact values. It can be determined, it's precise, it's accurate, and it's something we know. Quantum mechanics. Now, it's the branch of physics that correlates with the very small in the universe. It studies the behavior of matter and energy on the smallest levels. It's at the atomic level. It looks at electrons and protons and the atom itself, the nucleuses, and how they work, how the particles work, their behavior, their position. And it's also called quantum physics or quantum theory. This differs from classical mechanics because they use different principles. What controls classical mechanics does not control the extremely microscopic systems. And it's based on probability, which results in some very strange conclusions about the physical world. At the scales of atoms and electrons, many of the equations of classical mechanics, which again describes how things move at everyday sizes and speeds, stops being useful. Objects exist in a specific place at a specific time in quantum mechanics. No, my bad. Objects exist in a specific place in a specific time in classical mechanics, and they do not in quantum mechanics. They exist in a haze of probability. They have a certain chance of being at point A, then they're at point B, or vice versa. Certain properties such as position, speed, and color can sometimes only occur in specific set amounts. Now, this counters a fundamental assumption of classical mechanics, which said that such properties should exist on a smooth continuous spectrum. Particles and waves. Matter was believed to have come in two forms back then, particles and waves, and they still believe that now mainly. Particles are very small objects that make up the matter. It's the electrons and the photons, packets of light. Waves are a means of transferring energy to another location through a medium without actually transferring the physical matter itself. So this brought the question, is light a wave or a stream of particles? In other words, light may shine everywhere but may only hit one place, which explains interference and diffraction. This is called wave-particle duality, which we will get to later in the video. Because light can sometimes behave as a particle, this was initially met with serious criticism as it ran contrary to 200 years of experiments showing that light behaved as a particle. So people were mind blown. Light behaves similarly in that it bounces off walls and bends around corners, and that the crests and troughs of the wave can add up or cancel out. Adding wave crests result in brighter light, while waves that cancel out produce darkness. The color emitted corresponds to the distance between the crests, which is determined by the speed of the ball's rhythm, or the object's rhythm, or the particle's rhythm. Quantum mechanics developed over many decades, beginning as a group of controversial mathematical explanations of experiments that classical mechanics could not explain. It began at the turn of the 20th century, around the same time that Albert Einstein published his theory of relativity, a separate mathematical revolution in physics that describes the motion of things at high speeds. More specifically, on December 14th, 1900, Max Planck, who was a German physicist, published this paper on the effect of radiation on a black body substance. Now, a black body substance is any ideal black substance that absorbs energy without reflecting any of it, such as perhaps a black hole, which is why we cannot see them. Planck theorized that energy is made up of individual units, which he called quanta. His theory helped explain light absorption on the atomic level, behavior of heat in solids, and other unexplainable phenomena. He received the Nobel Prize in 1918 for his study on black body radiation. And while let's talk about what he wanted to find out, why he proposed this experiment. What he did was he sought to explain the distribution of colors emitted over the spectrum in the glow of red and white hot objects such as your light bulb filaments. When trying to make sense of the equation he derived, Planck realized implied that combinations of only certain colors were emitted, specifically those that were whole number multiples of base values. This means colors were quantized. This was very unexpected because light was understood to act as a wave, meaning that values of colors should be a continuous spectrum. This seemed so strange to Planck that he actually regarded quantization at first as nothing more than a mathematical trick that was playing on his mind and his vision. Planck's law describes the spectral density of electromagnetic radiation given off by a black body substance in thermal equilibrium at a certain given temperature. Now, in theory, you should only be able to measure extremely small distances is restricted only by how far you're willing to go. If you keep doubling a distance that is large, then the distance you can measure is limitless. But what happens if you do the reverse and try to measure something that keeps getting smaller? This is where the Planck length comes in. It's so small that it has 34 zeros after the decimal point. It is literally 5.3 feet divided by 10 35 times over, which results in a number that has 35 zeros after the decimal point. This is when classical mechanics become useless because it's so small. It can't be used to describe gravity, space, time, or particles. Planck time, it splits the second to a point that is no longer measurable. It's the equivalent of 10 to the negative 43rd seconds, which is a very, very small number. There are more Planck times in 1 second than there have been seconds in the universe since it began. 1 Planck time is the amount of time that it takes a photon of light to cross a distance of 1 Planck length. Anything that should happen before the hands move on the Planck clock, move by 1 unit, is unmeasurable, which allows many strange phenomena to take place. Albert Einstein, when quantum theory was first published, he had many problems with it. He didn't understand it, and it was just a strange, elusive concept that didn't make sense to anyone, and even today it still barely makes sense to most people. He tried very hard to disprove it, but eventually he realized it was necessary. In a paper I found, he wrote, "In what follows, I shall explain briefly why I consider the methods of quantum mechanics fundamentally unsatisfactory. I want to say straight away, however, that I will not deny that this theory represents an important, in a certain sense, even final advance in physical knowledge. I imagine that this theory may well become a part of a subsequent one. In the same way as geometrical optics is now incorporated in wave optics, the interrelationships will remain, but the foundation will be deepened or replaced by a more comprehensive one. And it has. We've had about 100 years now of experiments by many scientists, and quantum mechanics has gone very far. It's led us to many things we have today. Even this computer that I'm using is created by quantum physics. In 1900, Einstein theorized that not only was energy quantized, but the radiation itself was also quantized. Niels Bohr. In 1913, he proposed a theory for the hydrogen atom based on a quantum theory, that energy is only transferred in certain quantities. Electrons move around the nucleus, but only in directed orbits. As we see here, they are in certain orbits. They can only level possible, or this shows the quantum jump of an electron from one energy level to another. This is a hydrogen atom, and only certain energy levels can be achieved by a photon or an electron of light, actually. Whenever a group of atoms are being excited, for example, by heat, then electrons are changing energy levels and light is being given off. That's why you see light. The light from fire or from a stove is light that is being emitted by excited electrons. That's very cool. The process of moving from one energy level to another is called a quantum leap. Bohr's theory could explain why atoms emitted light in fixed wavelengths. Louis de Broglie. In 1924, he proposed that there is no significant difference in the makeup and behavior of energy and matter. On the atomic and subatomic level, either may behave as if made of either particles or waves. This is what led to wave-particle duality. It's very fundamental to quantum physics, and it states that particles often exhibit characteristics of waves, allowing them to sometimes act like particles and other times act like waves. It has a mind of its own, really. Werner Heisenberg. In 1927, he proposed that precise simultaneous measurement of two complementary values such as the position and momentum of a subatomic particle is impossible. Some argued with this, some agreed with them, but they moved on with it, and contrary to the principles of classical physics, their concurrent measurement is inaccurate. The more precisely one value is measured, the more inaccurate the measurement of the other value will be. This theory became known as the uncertainty principle, in which Albert Einstein famously said, "God does not play with dice." What is quantized energy? I've said this a few times already. Well, this is a very hard concept to explain, so I'm going to do my best to do so. Light comes in discrete packets of energy, in which we call photons. Photons of light move at the speed of light, obviously. They come in different sizes, and they correspond to different types of visible light and electromagnetic radiation. Smaller wavelengths have more energy in a photon, as there are. Anybody who knows about waves, smaller waves with, frequencies have more energy. Bigger ones, not so much. As you approach the UV range and above, the amount of energy in a photon of light becomes so high, electrons can actually be knocked off their orbital when energy absorbed. This is what is meant to be said when you say something is quantized. The Higgs boson, a phenomenal idea. In the 1960s, there was a gap in the standard model of particle physics. The standard model provides explanations and makes predictions about quantum physics. It couldn't explain. Now, before I go on, standard model is not a proven thing. It is more of a theory, but it is a model, and it's what's used from many experiments, and it has led to many proven theories. Now, it couldn't explain why the fundamental particles have mass, which was a problem. It also couldn't explain antimatter or anti-gravity or black holes, but no model is perfect, and that's also more quantum than it is standard. The standard model suggests that all fundamental particles should have been created in the Big Bang without any mass, but that's not true because we were finding many particles that were having more mass than they measured with. There was something that was giving them mass that we were missing, which is where the Higgs field comes in. It acts like an invisible force field that interacts with the fundamental particles to give them mass. The Higgs boson acts as a messenger to give the effect of the force field to the particle. The greater the interaction, the more mass the particles will have. Now, how does this work, though? Well, the Higgs field is in a room filled with particles here. This is a Higgs field, red line. These other ones are Higgs bosons, and they're spread evenly around the room. We have a quark here, and let's move on. When the top quark enters the room, the bosons gather around and slow the top quark down. The top quark loses momentum and energy but gains mass. There's a lot of interaction between the particles in the field. As we see, the quark moved in and now gathered a bunch of bosons around, and they're interacting and they're gaining mass. Now, when an electron enters the room, this blue guy here, the bosons ignore him and they move away. There's a little interaction, a little mass gain, but when a particle interacts with the Higgs field, the more energy it loses, but the more mass it also gains. So you trade energy for mass. And that's where this empty mass was coming from that we couldn't find. It was invisible. It was just there and we didn't know. Higgs boson is what explains that. Now, here we have what's called the double slit experiment. It's something that had a very big effect on quantum mechanics. Here we have a piece of paper down here, And we have a little slit here. We have one slit, all right? So this is what happens when you shoot light particles or photons through a slit in a piece of paper. They pass through the slit and leave one vertical line of marks where they hit the detector, as we see. Electrons are moving in here, the photons, particles, and this is where they were hitting. The detector picks them up. Now, what happens if we add a second slit? There would just be two vertical lines, right? Wrong. There are many lines. But how could this happen? As we see, two slits, but we have, here I only drew 4, but there would be many, many different lines. That wouldn't make sense, right? Because they would go straight and hit. I mean, only these two lines should be here. Where do the other ones come from? Well, the explanation for such an event is that particles are behaving like waves. When a wave passes through two slits here, it spreads out and then overlaps each other. When the peak of one wave meets the peak of another wave, actually, when the peak of one wave meets the trough of another wave, they cancel each other out. But when two peaks meet, they brighten. Like right here, these are areas where they brighten, they meet, and the effect is multiplied. This creates a pattern that's identical to the lines left by the particles. It gets even weirder than that, though. If you fire one particle at a time through the slits, as we see here, boom, it would have to go through both slits at the same time, because you will still get many, many vertical lines, not just two or one. That means it has to be somehow splitting and going through both of them at the same time while still retaining its mass. And even still, if we install this particle detector here, the detector will see a particle pass and it will beep. Now, as we showed, we only end up with two lines. This is a strange part of quantum mechanics. When you observe something, it changes. Just watching something changes the behavior. You know, particles act a certain way, but then when you watch them, they act a different way. It's almost like they're lying to you, trying to cover something up. Now, moving on, we have superposition. At the state of the quantum level, matter doesn't exist in a fixed state. Rather, it is a cloud of probability called a wave function. Therefore, matter exists in multiple states, which is called superposition. A particle wave is spread over an area and has no definite position, but it does have a direction. That's important. As a wave, a particle's direction of travel can be determined, but the position cannot be, because it's so small and whatnot. If the position of a particle is attempted to be measured, the wave function collapses and the direction of travel can no longer be measured. Being unable to measure all of a particle's properties is known as Heisenberg's uncertainty principle. Now, we have a guy here. His name is Aaron Schrödinger. Perhaps you heard of him. He's famous for his cat idea. And well, what really happened with that is that it's a thought experiment. This didn't actually happen. It's not a real thing. It's just a thought experiment created by an Austrian physicist, Schrödinger, to demonstrate how absurd quantum mechanics is, and it really did. It was designed to point out a flaw in the Copenhagen interpretation of superposition, which Niels Bohr and Heisenberg came up with. What happened before we get there, Schrödinger created this mental experiment in 1935 to show the paradox between what quantum theorists believe about the nature and behavior of matter on the microscopic level and what the average person might see on the macroscopic level with the unaided human eye. Now, what happened is that a living cat was placed into a steel chamber along with a hammer, a vial of hydrocyanic acid, and a small amount of radioactive substance. Now, if any of the radioactive substance decays during the test period, the hammer will break the vial. It will be prompted to break the vial of poison and cause the cat to die, right? Well, not technically, because what the thought is here is that you don't know whether the cat is actually dead or alive before you open the box. The Copenhagen interpretation of quantum physics was created by Bohr and Heisenberg. They proposed that atoms or photons exist in multiple states that correspond with different possible outcomes and positions and do not commit to a definite state until they are observed. That goes against what many other people believed. Schrödinger designed this thought experiment to show us that the Copenhagen interpretation would look like is the mathematical terminology used to explain superposition, and the microscopic world was blown up to a macroscopic level that an average person could understand. And he did so. In the experiment, the observer doesn't know whether an atom of the radioactive substance has decayed and does not know whether the vial has been broken and if the cat is dead. According to the Copenhagen interpretation, the cat will be both dead and alive until someone looks into the box. In quantum mechanics jargon, the cat's ability to be both alive and dead until it is observed is called the observer's paradox. The logic behind the paradox is the proven ability of observation to influence outcomes or possibilities. This is the weird part of quantum mechanics. Particles behave differently when you observe them, as I said before. Physicists don't know why this is, but perhaps someday they will. His thought experiment was intended to make people ask themselves if it was logical for observation to be the trigger. Wouldn't the cat be either dead or alive, even if not observed? Generally, we would say yes, but quantum mechanics says otherwise. It's very confusing. In what's known as the many worlds interpretation of quantum law, the cat is both alive and dead. This means that the observer and the cat exist in two realities, one which the cat is dead and one which the cat is alive, which we will get to in a minute. Parallel universes, the many worlds theory, as I just mentioned. It was created by Hugh Everett, and he agreed with much of what Bohr had suggested about the quantum world. He accepted with the idea of superposition as well as wave functions. However, there was one aspect that he disagreed with Bohr on. To Everett, measuring a quantum object does not force it into one fixed state or another. He believed a measurement was taken of a quantum object, and it causes a split in the universe. The universe is literally duplicated, where it splits into one universe for each possible outcome for the measurement. This is what is meant by dual reality, such as Schrödinger's cat. For example, an object's wave is both a particle and a wave. When a physicist measures a particle, there are two possible outcomes. It will either be measured as a particle or a wave. If you were given a life or death situation and you lived in this situation, there would be an exact identical parallel universe where you actually did die and you don't even know it. Now, what gets even weirder is what's called quantum suicide. And no, this isn't the suicide of an atom or a particle or an electron. It's a thought experiment created by Max Tegmark in 1997. The scenario is that a man has a special gun that's tied to a machine inside the gun, and it measures the spin of a quantum particle, which is called the quark. When the trigger is pulled, the spin of the quark is measured, and the gun may or may not fire depending on the measurement. Now, if the quark spins clockwise, the gun will fire and the man will be dead. But if the quark spins counterclockwise, the gun will not fire. There will be a click, but nothing will come out. No bullet. He won't be alive. And when the man pulls the trigger, let's say the gun doesn't fire. He'll click it again and again and again and over, but it will never fire. So, but the bullet will never fire. It will never come out. He will never die. He'll just keep going over and over again. Now, let's say the quark did measure as spinning clockwise and the gun did fire. The man is dead. But wait, the man already pulled the trigger the first time an infinite amount of times following that. And we already know that the gun didn't fire. How can the man possibly be dead? The man is unaware, but he's actually both alive and dead at that moment. Each time he pulls the trigger, the universe is split in two into a dual reality, and it will continue to split again and again and again each time the trigger is pulled. So there will always be a universe where he dies and a universe where he lives. As I said, it's just a thought experiment created by someone at Yale. Quantum entanglement. Very interesting theory. It gives two photons, we place them next to each other and they will perform precisely opposite actions. particle A will spin up while particle B will spin down. If we place them as far apart as we can to the very edge of the universe, one on the way to the left of us and one to the way on the right of us, this will still occur. They will still have opposite actions at the same time, as if they're seeing each other right there, as if they have instant communication or something. This is called quantum entanglement. And Einstein referred to this as spooky action at a distance. And I don't think when he said that he actually realized how spooky it was. Quantum entanglement defies the rules of physics, that nothing can travel faster than light, that objects are only influenced by their immediate surroundings. Physicists can explain the link between particles, but they somehow can communicate right then and there, instantly, whether they're right next to each other or they're thousands and millions and billions and trillions of light years away from each other. Which leads to the idea that we couldn't use this to have instant communication one day. However, there's much argument about this because it's theorized that quantum entanglement doesn't allow classical information like what we do to travel faster than light. There is that only particles can use it to transfer their information to each other. Quantum tunneling. It refers to quantum mechanical phenomenon where a particle tunnels through a barrier that is classically, as in classical mechanics, could not surmount. This plays an essential role in several physical phenomena, such as nuclear fusion that occurs in main sequence stars like the Sun. It has important applications to quantum computing and describes radioactive decay in which the helium nucleus emits an alpha particle. Now, here we have an electron field. It's not going to go through, right? It's going to bounce back, right? Electron wave. In quantum physics, it's possible that this wave might go through. So, what this means is that the equation which describes quantum particles is Schrodinger's equation, and its solutions are wave functions. What happens when a wave like this hits an energy barrier? Well, the wave doesn't have enough energy to go over the barrier, right? If this were classical mechanics, the particle, let's say a ball was running up the hill, right? That would be the end of the story. Right? If you're standing on one side of the hill, you throw the ball, it goes down, and it's only going to go as high as you are and before it comes back. Everyone knows that. That's simple mechanics. That would be the end of the story. Kinetic energy was converted into potential energy, and at some point the kinetic energy runs out, the ball stops and rolls back again. The ball can only roll as high as you are from when you dropped it, unless you shoot it out of a cannon or something, which with extra power, then it might go over. This is the law of conservation of energy. But if it isn't quantum mechanics, the ball follows Schrodinger's equation and could end up in the middle of the hill, or even on the other side of it. This means the probability of finding the ball, which is determined, by the way, by wave functions, drop dramatically. So if the hill is not infinitely high or infinitely thick, there's a small probability that the ball will actually make it through to the other side, as though it has tunneled through, which is why we call it quantum tunneling. This also has an effect with the Sun. Helium is produced when two hydrogen atoms fuse together. We all know this, but however, this is extremely difficult to do. We can't even do this on Earth. We have to heat it up to about 100 times as the Sun does just to fuse atoms together. The two protons will repel each other, and an immense amount of force from heat is required to give them the energy they need to fuse. Even if the Sun isn't hot enough to give the protons the energy they need, quantum tunneling will help that. It's responsible for the fusion of hydrogen atoms. There's a small probability that one of the protons will cross the barrier and fuse with the other protons. It helps the Sun burn and go on. Quantum teleportation. Using the property of quantum entanglement, we can teleport objects between two particles. What is meant by this is that your body is scanned and the information is transmitted somewhere else and used to build a new body out of different materials. Very interesting, right? Well, let's see how it works. If we take two particles, entangle them, and send one to the moon, and keep the other one here on Earth by us, then we can use quantum entanglement to teleport something between them. The actual process to do that is obviously more complex than that. intricate. It requires math, a careful setup, and lots of observations. Then we can teleport a selected object. After that, you have to make an observation of the object you want to teleport, which sends information to the other entangled particle on the moon. Then your object is teleported, but you have to have the raw material to do so, obviously, otherwise you're not going to get anything. You have to have material to make something. So it's basically sort of works like a machine. It makes something. You send something to it, and it makes it just quicker and instantly, and across a long distance. Of course, teleporting large objects or people is most likely never going to happen in the near future. Keeping particles entangled for a long period of time over long distances or along with objects larger than a few atoms is far out of our reach with current technology. However, this experiment has been performed multiple times with small particles in labs around the world, and scientists have managed to teleport various electrons, photons, and even entire molecules across many, many miles. The string theory. Quantum mechanics and Einstein's theory of general relativity, they don't coincide. They're incompatible. They defy each other. Because quantum mechanics describes space as being quantized, while general relativity describes space as being a space-time continuum, as Einstein said. Now, the string theory attempts to fix this, and it describes space as one-dimensional objects called strings, and they're like fabrics of the universe. However, this is an entirely new idea and concept that would require a whole nother video to explain. So, that is about quantum mechanics simplified. Thank you for listening. My name is Stephen Velick, and have a good day.